Continuous internal mixing is the term used to describe the straight-through mixing process which takes place within this two-component mixing chamber, whereby each incoming drop of material A is mixed with a companion drop of material B by the force of injection of the two liquid streams simultaneously entering the mixing chamber. The on-off spray action is determined by the position of the movable valving rod within the mixing chamber. The off position corresponds to the forward position of the valving rod, where it fully occupies the mixing chamber. When the gun is triggered, the valving rod moves to the spray position, where the injection slots at the rear of the mixing chamber become uncovered. The location of these slots, the same slots into which the cleanout spade must be inserted if a clog has developed, and the injection force of the two liquids as they enter the mixing chamber create a swirling, turbulent motion which continuously and completely mixes the liquids before they leave the mixing chamber. Understanding how continuous internal mixing takes place, you can see that if a momentary pressure failure or interruption of flow occurs with one material but not the other, then that portion of material that enters the mixing chamber without its companion portion will be sprayed off ratio. Whoever operates a two-component spray gun must learn to respect the ratio requirement, for this is what creates the predetermined finished foam properties that a chemical formulation is intended to have. Of nearly equal importance to the spray gun in the foam production process, therefore, are the proportioning pumps, needed to control ratio and sustain continuous flow of both materials to the gun. The operation of these positive displacement double-acting piston-type pumps, demonstrated with this visible model, shows that the trick to the design which causes it to pump liquid forward on both the upstroke and the downstroke is the establishment of a chamber in the upper half of the pump, which increases in length as the piston moves downward. Liquid flow from the lower chamber holds the inlet ball valve closed, forcing liquid flow past the discharge ball valve toward the output, where some liquid flows forward out of the pump and some flows upward to fill the upper chamber. When the piston reverses, flow out of the upper chamber pushes the discharge ball valve closed, forcing flow forward out of the pump. The high-pressure liquid holding the discharge ball valve closed is isolated from the low-pressure lower chamber, allowing liquid from the material supply system to push the inlet ball valve open and refill the pump. By making the cross-sectional area of the piston rod 1/2 that of the cylinder, as the piston is pushed downward, the upper chamber increases in volume at 1/2 the rate that the lower chamber decreases. Therefore, on the downstroke, exactly 1/2 of the output from the lower chamber flows to the upper chamber, and exactly half flows out through the outlet. On the upstroke, the half which filled the upper chamber flows outward as the lower chamber refills. The volume of liquid pumped forward on a complete cycle is called the displacement of the pump and is determined by the pump's dimensions. The ability to pump an equal predetermined volume of fluid on each cycle, the feature which is referred to as positive displacement, is made possible by the effectiveness of liquid seals within this piston pump, which prevent internal leakage and recirculation of liquid between the high-pressure outlet and low-pressure inlet, assuring delivery of the full volume for which the pump was designed. Two positive displacement pumps, driven by a common drive system, provide accurate ratio control of one liquid volume to another. Pump displacement is clearly indicated by numbers stamped on piston shafts and pump cylinders. Identical pump dimensions give a 1-to-1 volume ratio. Replacing one pump with a pump of different dimensions as required to obtain a particular ratio for a different chemical formulation makes many volume ratios possible. To fulfill the requirements of mechanical thrust and efficient liquid seals necessary to develop working pressures of up to 1,000 pounds per square inch, the design of actual production proportioning pumps is somewhat different than the visible model demonstration pump used thus far, and is more accurately represented by this visible model where piston shaft and pump cylinder are located at the end of the pump base, allowing two piston shafts to be brought into close alignment with the thrust of the common drive system. The inlet ball valve on the rear side of the pump base and the discharge ball valve on the front side of the pump base are guided directly over the ball valve seat by a clover-shaped insert, which aids in rapid ball valve seating during pump reversals. A screen placed at the pump inlet before the ball valves filters solid particles which would lodge in the ball valve seats and prevent 100% liquid sealing. The mechanical makeup of these piston pumps makes it virtually impossible for proportion to drift as long as they are completely filled with liquid on each fill stroke from a material supply system such as these transfer pumps. From a pump standpoint, there is a tremendous difference between pumping non-compressible liquid and compressible air. Compressibility versus non-compressibility can be demonstrated by two identical piston and cylinder assemblies, one filled with air and the other filled completely with liquid. The force required to develop 15 pounds per square inch in the liquid cylinder causes no movement of the piston into the cylinder, and the gauge reading rises rapidly. The liquid does not compress as force is applied. The same force applied to the piston of the air-filled cylinder causes considerable movement of the piston into the cylinder, and the gauge reading rises slowly. Air does compress as pressure increases when force is applied. This cushioning, spring-like effect of air, if trapped below the piston, would tend to interrupt constant flow and reduce the displacement of the proportioning pump by allowing some downward motion of the piston before liquid flow begins. Entrapped air must be compressed until pressure in the lower chamber equals the high pressure holding the discharge ball valve closed from above before outward flow can begin. A self-purging air bleed fitting on the bottom of the piston purges air from the lower chamber, and by placing the side connection to the upper chamber at the very top, the entrapped air is automatically purged from the pump with the outward flow of liquid. Another way in which the pump can be incompletely filled results from lack of incoming flow, causing the piston to rise faster than the liquid level. This is called cavitation, describing the cavity or void which develops below the piston. Cavitation, demonstrated with a liquid-filled cylinder where the piston is pulled upward away from the liquid level, shows that the cavity is actually a low-pressure vacuum which tends to collapse rapidly, drawing the piston inward before liquid pressure can be developed. The result of cavitation in a double-acting pump is somewhat similar to the effect of entrapped air. Interruption of constant flow occurs at the top reverse. The piston must close the cavity before outward pressure can be developed to push the discharge ball valve open. Because of the common drive system on the proportioning unit, however, multiplying effects develop which make even the slightest amount of cavitation detectable by the observant foam mechanic. In slow motion, notice that during the no-pump portion of the stroke in the cavitating pump, the second pump in the common drive system immediately begins pumping after the top reverse, resulting in momentary loss of ratio control and imbalance of material pressures. The pressure loss in the cavitating pump is accompanied by a pressure increase in the opposite pump, since the cavitating pump offers no resistance to the common drive system as the cavity is closed, and the total driving force is applied to the second pump, which therefore tends to double its output pressure, increasing the effects of pressure imbalance. Still, another multiplying effect develops when cavitation occurs because of the pump's double-acting design. Since the lower chamber is not completely filled on the upstroke, the half of its output, which normally fills the upper chamber, does not exist. The half instead flows back from the outlet hose as if pumping action were in reverse. The extreme unbalanced pressure situation caused by the multiple effects of cavitation appear at the gun as irregular pulses of off-ratio material in the spray pattern, indicating lack of material flow to the proportioning unit, and more serious problems to follow if spraying is not immediately stopped and the material supply problem identified and corrected. Experience has shown that most material supply problems are due to three predominant characteristics of the liquid foam components. To avoid the needless problems which would be encountered by a person unfamiliar with these characteristics, the foam mechanic must be fully aware of the temperature sensitivity of resin and isocyanate, the liquid blowing agent which will escape from the resin at temperatures above 75 degrees Fahrenheit, and the reactivity of isocyanate with moisture in order to control material temperature and eliminate humidity problems when dealing with the liquid components of foam.